Now in this video, we're going to talk about the unit circle. The unit circle is a third way that we can define trig values of angles. So we had right triangles, which were good for acute angles. We had quadrants and reference angles, which is good for any angle in the plane. The unit circle is another way that we can find very easily the trig values of angles in the plane that have very nice reference angles. So first off, the unit circle is defined to be the circle whose equation is x squared plus y squared equals 1. Okay, so that means that the circle has a center at the origin and the radius of the circle is 1. Okay, so we're going to intersect the x-axis at x equals 1 and x equals minus 1, the y-axis at y equals 1 and y equals minus 1. So again, here our radius is going to be equal to 1. Okay, so how do we tie this into angles? We can think about this two different ways. So the first would be if we had some angle theta in the plane, the terminal side of that angle is going to intersect the unit circle at some point. Okay, let's say that point is x comma y. Well, the radius of our circle, again, is equal to 1. Therefore, what we were calling r in the previous section, the distance from the origin to our point on our terminal side, is equal to 1. Okay, so what that means is that, recall, cosine theta for any angle in the plane is defined to be x over r. Sine theta is defined to be y over r. Well, if r is equal to 1, these become cosine theta equals x and sine theta equals y. Okay, therefore, there's a correspondence between a point on the unit circle and the cosine and sine of an angle in standard position. This is one way to look at it. Another way would be if theta were in radians, and generally when we work with the unit circle, we do talk about angles in radians. It becomes a little bit more natural. Recall that the arc length of the intercepted arc is equal to r times theta. Well, if r is equal to 1, this becomes s equals theta. In other words, if we allow for arc lengths greater than 2 pi and negative arc lengths, we can also think about theta as being the length of our intercepted arc on our circle. So there are two different ways we can think about it. Either is fine. I think to start is probably more natural to just think about this picture of a terminal side intersecting the circle. Regardless of how you think about it, there's this correspondence between points on the unit circle and trig values of angles. So whenever we talk about the trig functions on the unit circle, not only is it the case that x is cosine theta and y is sine theta, so we can define sine theta to be y and cosine theta to be x. Okay, just like before, tangent theta is going to be y over x. It'll be sine over cosine. Now cosecant will become 1 over y. Secant theta will be 1 over x. And cosecant theta will be x over y. And one of the nice things about the unit circle is that it does streamline the definitions of the 6 trig functions a little bit, because now our r value is equal to 1, so we don't actually really have to worry about the r. Now it's just sine is y, cosine is x, tangent is y over x, and then we can use our reciprocal formulas. One thing you do have to be careful about when you are doing sine and cosine using the unit circle. Usually when we talk about trig functions, for traditional reasons, we usually think of sine before cosine. We'll say sine first, then cosine. That's generally just the order in which we write them. However, when we're doing coordinates in algebra, we do x before y. So just remember that the sine is y and the cosine is x. It might be kind of backward from what you might expect. Okay, so for example, let's suppose we have a point on the unit circle. That point is going to correspond to some angle, and we want to find the trig values of that angle. So let's suppose that the point 1/4, y lies on the unit circle. In quadrant 4, and the point is going to correspond to some angle. So we'll just say theta. And let's suppose we want to find, well, let's just find sine theta. Okay. Note that we have cosine theta. Cosine theta is 1/4. Let's go ahead and find sine theta, which would be our y value. Okay, using the unit circle, we can employ the fact that on the unit circle, x squared plus y squared equals 1. So 1/4 squared plus y squared is equal to 1. So 1/16 plus y squared is equal to 1. Therefore, y squared is 1 minus 1/16 is 15/16. And therefore, y, now we take the square root of both sides. Since we're in quadrant 4, y is going to be negative. Therefore, y is going to be the negative square root of 15/16. Or negative the square root of 15/4. And since the y-coordinate of our point is the sine value of the corresponding angle, we get that sine theta is negative square root of 15/4. And then once we have the sine value, of course, we can find the tangent. We can do y over x. We can find the cosecant, secant, and cotangent using the appropriate identities. Note that this is a problem that we could do without using the unit circle as well. If we're given that an angle is in the 4th quadrant and has a cosine equal to 1/4, we could also draw a right triangle in the 4th quadrant. We could use Pythagorean identity. So this is just another way to get at the same sort of problem. Okay, now to finish up our discussion of the unit circle, I'd like to show you how we can use the unit circle to very quickly recreate our chart of elementary trig values. So the trig values for our common angles all the way around the circle. Okay, so I'll start with our quadrantal angle, 0, pi over 2, pi, and 3 pi over 2. Okay, I will add to those the angles that lie at multiples of pi over 4. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, and then we have the angles that lie at multiples of 30 degrees. So pi over 6. 5 pi over 6. 7 pi over 6. And 11 pi over 6. Okay, and then finally our pi over 3 angles. Pi over 3, 4 pi over 3, 2 pi over 3, I should say. 2 pi over 3. 4 pi over 3. And 5 pi over 3. Okay, so those are all of our angles. Okay, and I'm just going to do the first 2 quadrants here just in the interest of time and leave it for you to fill in the rest. So first off, the positive x-axis will intersect the circle at the point 1, 0. That corresponds with the fact that the sine of 0 is 0, the cosine of 0 is 1. Now moving to the angle pi over 6, its cosine value is square root of 3 over 2. Its sine value is 1/2. So we're going to be at the point square root of 3 over 2, 1/2. Moving to pi over 4, the sine and cosine values are both equal to 1 over square root of 2. Then moving to pi over 3, the cosine value is 1/2. The sine value is square root of 3 over 2. So we see that as we start to move around the circle, the y values are going to be increasing where the x values are going to be decreasing. Once we go up to the positive y-axis at the angle pi over 2, now x is 0, y is 1. Once we get this quadrant of the unit circle drawn out, we can use a little bit of a shortcut, and that is that the unit circle, being a circle centered at the origin, has symmetry across both the axes. So we're symmetric across the y-axis, we're symmetric across the x-axis. So that means to get the point for 2 pi over 3, we can just take the point for pi over 3 and reflect it. And that's going to just turn the x-coordinate negative. Okay, so now the point becomes negative 1/2 positive square root of 3 over 2. Okay, similarly, to get the point for 3 pi over 4, we can reflect the point for pi over 4. So this is going to become x equals a negative 1 over square root of 2, y equals positive 1 over square root of 2. And for 5 pi over 6, we can reflect the point for pi over 6, and our x-coordinate becomes negative square root of 3 over 2, positive 1/2, and then for the point at the angle pi, the coordinates become negative 1, 0. And like I said, I will leave the rest for you to fill in here, just in the interest of time. But note now, to get the third quadrant angles, we can take the second quadrant angles and further reflect them across the x-axis. Okay, so now we're going to take the negatives of the y-coordinates as well. And then to get the fourth quadrant angles, we can reflect the third quadrant angles back across the y-axis, which is going to turn the x-coordinates positive again.